already saw the first application of Gaussian elimination is to understand the properties of the matrix. The second one, we could say that we can determine the solvability conditions of the system of linear equations that a matrix represents. We can actually go one step further and actually solve the system. We shall see that very soon. Then there is what we call a matrix factorization. A matrix, given matrix A, can be written as a product of two matrices, and that way of factorizing a matrix turns out that has quite a few applications in machine learning and also in theoretical linear algebra. So all these applications as of now might sound kind of mathematical or academic in nature, but the actual computer sciencey things will follow. They're not too far behind. Let's take a look. Pivots and ranks. Pivot is the first non-zero element in a row of a matrix after you have put the matrix in the Row-Echelon Form, REF, so that you get pivots right away. And then you know that the number of pivots is the rank of the matrix. Then there is this idea that the row rank, which is what you get by applying the elementary row operations and getting to the REF, that process is also called row reduction. And a column rank, if you were to apply elementary column operations and then get to the pivots, you will get the same number. That is not completely obvious when you put it this way, but it is true. Then we also saw the property that a rank cannot be more than the number of rows, neither can it be more than the number of columns. So in mathematics lingo, succinctly, you can write it as a rank of A is less than the minimum of its number of rows or columns. Minimum of m and n for a matrix that is a member of R m by n. Rank cannot be greater than the number of unknowns, which would be the number of columns. Rank cannot be greater than the number of equations. That would be the number of rows. If the rank happens to be the number of unknowns, providing that the system is consistent, then you have a unique solution. If it's a square matrix, and if you have the rank to be the number of unknowns, number of columns, that means number of rows also the same. That means all equations represented by the matrix are independent and consistent, and that situation is the ideal situation, unique solution. But life, as usual, is far from ideal, so you will never see this ideal situation in practice in computer science or in data science. Now, determinant, as we saw last week, is one number that can say a lot about the matrix. The row operations that we perform on A to get to its REF, there are three row operations. We are trying to use only the third one, which does not change the determinant. But if you have to use the first one, which would be swapping of the rows, then that does change the sign of the determinant. So the absolute value of the determinant doesn't change as you apply the row operations to get to REF. So right away, if you compute the determinant of the REF, we're talking about a square matrix here because we're talking about determinants, then the determinant of the REF is going to be the determinant of the original matrix modulo the sign. Now, if you were to compare the properties of the determinant and the row operations that we perform, you can see there is a similarity. Now, for a triangular matrix, the determinant of a triangular matrix is the product of the diagonal elements, because you just have to expand along the top row if it is a lower triangular matrix, along the first column if it is an upper triangular matrix. So it's obvious that the determinant is just the product of the diagonal elements. And when you perform the row operations to get to the Row-Echelon Form, what you're getting is an upper triangular matrix. We saw that in our visualization, and you can keep trying it for different matrices and you will see that it has to be that way. And by the definition of pivots and the definition of the Row-Echelon Form, you know that it has to be an upper triangular matrix. The fact that the first non-zero element in any row has to be to the right of the first non-zero element in the row above it will imply that it's an upper triangular matrix. It turns out that performing Gaussian elimination followed by a multiplication of the diagonal elements is the most efficient way of computing the determinant. As we saw, the Laplace formula for the determinant, though mathematically compact and elegant, from the perspective of implementing it in a computational fashion, is horrible. So it is always implemented using Gaussian elimination. or at least row operations. It turns out that when I ask you a question in the exam also, if I give you a matrix, typically a matrix with some variables inside, and ask you some question about the determinant, your best strategy would be to actually perform Gaussian elimination and then see what you can deduce from there. If you sit down and try to expand it using Laplace expansion, it will lead to complications that are best avoided. So computation of determinant, let's say this matrix, this as you can see is my favorite matrix of prime numbers. It is not easy to do it by Laplace expansion if you were to do it by hand. Even as a computer program, if you were to write nested for loops to do this, recursive determinant calculation, it's not efficient at all. Just find the row echelon form of A first. Once you do that, you get this, and now you can see that the determinant has to be the product of 1, 3, 4, and 50. Modulo a sign, we don't really know whether it's positive or not because we haven't kept track of the row swaps that you may have had to perform. If you do, if you actually keep track of row swaps, the so-called permutation matrices, a row swap permuting two rows, and that is called a permutation matrix, that will keep track of the sign of the determinant too. Now, one way of solving the equations is to perform row elimination. Then the last equation will look like the last variable can be read off directly, and then you can back substitute. Of course, Gaussian elimination has one of its primary goals as solving of equations. So this is the way you do it. So it's solve a system of linear equations, get the row echelon form first, but then how do you get the solution? And that process is called a back substitution. We will see that we can see that by just looking at the structure of the row echelon form. Remember, in the row echelon form, all rows with 0 elements, the 0 rows, are supposed to be at the bottom of the matrix. Those equations just read 0 equal to 0. So those things are useless. Of course, if there is any 0 equal to non-zero, then you cannot solve at all. Then you can just say that there are no solutions. From now on, we are talking about situations where you do have solutions. And the pivot of any row is strictly to the right of the pivot in the row above it. What that means is that row near the bottom will have one fewer variable in the equation corresponding to it than the one above it. That means you can keep back substituting to get the full solution. So you look at the last non-zero row, and that will give you the solution to the last variable. I know that these things sound a bit fuzzy at this point. That's because we don't have an example in front of us right now, but the moment you see an example, you will be home free. And then you back substitute in the row above to get the second last variable and so on. So let's take our simple example here. X plus y equal to 5, x minus y equal to 1. Then subtract row number 1 from row number 2. That gives you the matrix that you see on the right. So this is my original matrix, augmented matrix. And I perform REF on the augmented matrix to get this. And now just look at the second row there. The pivots, of course, are the first non-zero elements. There are two pivots. So it's a full rank matrix, full rank square matrix. That means unique solution. No 0 equal to non-zero. So everything is fine. The last row, if you translate that back into an equation, that just reads minus 2y equal to minus 4. So y equal to 2. So from the last row, you read off the last variable right away. Then you substitute that in the previous row, which reads x plus y equal to 5. Y we already computed to be 2. So x plus 2 equal to 5. X is 3. And that is the process of back substitution. If life was that simple, it would have been nice. But life is never that simple. It's far more complicated than that. So when n is greater than m, that means when the number of variables is more than the number of equations, or when the rank is smaller than the number of equations, you have too few equations. The system is not constrained enough. So you have what we call free variables. So those will make life quite interesting. So let's look at this one. X plus y plus z equal to 6. 2x plus 2y plus z equal to 9. So there are only two equations in R3 because there are three variables. So we are working in R3, X, Y, and Z directions. The first one forms a plane. The second one also forms a plane in a slightly different orientation. So these two planes will intersect and there's one line. So one line that will satisfy both these equations, and there's infinite number of solutions. The moment you have a free variable, the free variable can take any value. That's why it's called a free variable. And that will mean infinite number of solutions if the system is consistent. So let's write down the augmented matrix. 1, 1, 1, 6, 2, 2, 1, 9. Then let's perform elementary row operation. So subtract twice the first row from the last row. You get 0, 0, 1 minus 2, minus 1, 9 minus 12, that is minus 3. So this is what you get. So you have a pivot here, very good, and a pivot here, very good. So the column that doesn't have pivot, the variable corresponding to that, we can take that as the free variable, which means you can assign any value to it and then solve. So we'll assign any convenient value to solve. We have to find all possible solutions, and there will be a little bit more work to be done. So let's see how that is done. So 3 variables, X, Y, and Z, only 2 equations. So select Y as the free variable. Y, because that is the column that does not have a pivot. Non-zero equation just reads minus Z is minus 3. So Z is 3. So that just says Z is 3. And now back substitute in the previous line. So X plus Y plus 3 is 6. So X plus Y is 3. Now Y can take any value. So let's put Y to be T, any value. T is one convenient way of doing it. And if you had 2 free variables, then it would be T1 and T2. So if Y is T, then X is 3 minus Y, 3 minus T. So the solution would be X, Y, Z, 3 minus T, and Y was set to be T, and then 3. Then what you would do is to kind of decompose it into one vector, fixed vector, and one vector that is multiplied by T, scaled by T. So it looks like 3, 0, 3 and a T multiplying minus 1, 1, 0. So if you add them up, you will get this. And this decomposition is not actually very complicated. It's fairly easy to do. What this is saying is that when T equal to 0, when you set Y equal to 0, which you're allowed to do because it's a free variable, then the solution is 3, 0, 3. So X is 3, Y is 0, this is 3, so 3 plus 3 is 6. 2x, 6 plus 3 is 9 because Y is 0, so that's satisfied. This constant vector is called the particular solution, and this guy is called the special solution. The particular solution is arrived at by setting the free variable to 0. So if you just set Y to 0, then you have only 2 variables and then 2 equations. That's the solution to that. And to get to the special solution, what you will do is to set the value of the free variable to 1, if there is only one free variable, and set the right hand side to be 0. Why that happens that way, it's not easy for me to explain to you right now. It'll take some work, but we'll get there. So if I set Y to 1 and these two guys to 0, then again I have 2 equations and 2 unknowns. So Y is 1, this is 0. So let's write down the equations. This is 2 here, and can take that to the other side. Then you get 2x plus z equals to minus 2, x plus z equals minus 1. Remember, y has already been set to 1. Now let's ignore the first one because it's already solved, already set because it's a free variable. Let's solve the other two. Just multiply the first one by 2, subtract the second one from the first one. So minus 2 and minus 2 here also. So z turns out to be 0. Put z to be 0, x is minus 1. X is minus 1, z equal to 0. And y was set to 1 because we are allowed to. And that thing is called the special solution. Let's go through this once more just to give you the nomenclature. So I had 2 equations, x plus y plus z equal to 6, 2x plus 2y plus z equal to 9. Then I came up with a solution by virtue of the fact that y was free. I set it to a value t. Then from the first equation, after having solved for z, which was 3, from the first equation, I got x equal to 3 minus t. We saw all that in the previous slide. So finally, I got two components to the equation. One can take a parameterized scale version of a vector. The first one is a fixed vector. So the solution is of the form x, which is a solution, is x particular plus t times x special. The particular solution to the system when the free variable is set to 0. Y is set to 0. The special solution is something that can be scaled and added to the particular solution without affecting the solution. What I mean is, for any value of t, if you compute this vector, then substitute x, y, and z after computing the whole sum will satisfy that. So let's take t equal to 0. Obviously, it satisfies that because it's 3, 0, 3, 3, 0, 3, 6, 6, 0, 3, 9. Now let's take t equal to, let's say, 10. So x is going to be 3 minus 10, so minus 7. Y is going to be t times 1, so that is going to be 10 because we took t to be 10. Z equal to 3 plus 0, so that is 3. So what do you get? Minus 7, 10, 3, they add up to 6. Here 2x, x is minus 7, so this is minus 14. 2y, y was 10, so 2y is at 20. Z was 3. What does that give you? 20 minus 14, 6 plus 3. That also is satisfying. So it will always work that way, and that is why there is a solution. There's a line of vectors as a solution. So complete solution can always be written in this fashion. It's also called the general solution. It's a particular solution plus a special solution times a scalar. And if you have more than one free variable, then for each free variable you'll have a scalar and a special solution. So you will practice this using some examples in the textbook. So to put it down once more, the general solution is a particular solution plus linear combinations of special solutions. And special solutions are the ones that solve the equation, system of linear equations, ax equal to 0, meaning the constant vector is 0. And it's also called homogeneous system of linear equations. So for that reason, those solutions are called homogeneous solutions. We will have other names that we will use for these things later, and we will look at these things in different ways later. But of course, in this chapter in the textbook, you will have more information and examples. Please go through those. Now, coming back to the theory part of it, not the numerical computation part, each elementary operation, each ERO, elementary row operation, will correspond to a matrix. What kind of operation is an elementary row operation? It's a row operation. So we have the row picture of matrix multiplication. We are doing some row operation. So it's like multiplying the original matrix on the left by some matrix that will implement the row operation. Because by the row picture of matrix multiplication, you know that the product is a linear combination of the rows of the second matrix. We take the second matrix as our original matrix A and multiply on the left by something that will make the same kind of row operations. So that's what we want to do. So swap any two rows. So the second and third row, we will write it as R3 getting swapped with R2. Multiplying a row by a scalar, let's say R2 is getting replaced by 4 times R2, and this arrow to the left is usually read as gets. R2 gets 4 times R2. Adding a multiple of a row to another, that is something like row 3 getting row 3 minus 3 times the first row, or minus 3R1 plus R3. So we'll use a row picture of matrix multiplication. So we are looking for linear combinations of the rows of a matrix on the right. So on the left, we'll be multiplying by some elementary operator, which is a matrix, EI. So EI is for one operation. So we'll stack a bunch of them, E1, E2, E3, etc., multiplying A to finally get an upper triangular matrix, which is the row-echelon form. So EA, E being the product of all the elementary operations that will take you from the original A to U, which is a REF of A. First operation, second operation, and K operations like this. So let's look at our original set of simple equations. X plus y is 5, x minus y is 1. So subtracting row 1 from row 2, you get in the augmented matrix, when you perform that operation, you get pivots. We saw that. So how do you subtract the first row from the second row? Using some kind of an elementary operation. So let's look at this guy here. That is my row 1. I'm subtracting that from the second row. So I want to take linear combination of the rows, the red rows in the second matrix here. And what kind of linear combination am I taking? For the first row over here, I'm not doing anything. It's 1, 1, 5. It's here also is 1, 1, 5. So it's just the first row. There's nothing coming from the second row. It's just the first row that just gets pasted there. For the second row, I'm taking the second row of the red matrix and subtracting the first row from here, from the second row. So the second row is taken as it is, and then the first row is subtracted from it. So it's a linear combination of the rows. What kind of linear combination? Minus 1 times the first row plus 1 times the second row. That is R2 minus R1. That's what we wanted to do. So that's how you encode this. That is how you come up with the elementary matrix there. That sounds a bit complicated. Let me give you a shortcut. What you want to do is to apply the elementary operation you want to apply to the identity matrix. Let me explain. So I will take the identity matrix 1, 0, 0, 1. If you're working with two variables, that's the identity operator. I want to subtract the first row from the second row. If you perform that operation here, what do you get? I subtract the first row from the second row. Nothing happens to the first row. The second row, I subtract the first row. So it is minus 1 plus 0. The second part of it, I'm subtracting the first row from it, but first row is already 0. So it's 1 minus 0. So that resulting matrix is the elementary operation. So when I say it that way, you really think that this is some kind of a super secret shortcut. It is not. What it is that this matrix, what it is doing to the red matrix is also what it will do to any matrix. So E is going to do something to A, and we want to find out what that is. And if I apply E to I, it will do the same performance, same thing on the matrix I, the identity matrix. That is very easy to do as we did it here. But what is EI? EI is just E. So just apply the elementary operations on the identity matrix, and what you get is actually the elementary matrix corresponding to that particular elementary operation. Just in case you didn't catch that, let me say that once more. Apply the elementary operation to the identity matrix. What you get as a result of that operation is the elementary matrix corresponding to that operation. But using the row picture, which is a little fancier to actually explain, in my upper triangular matrix, that is the REF, the first row is 1 times the first row of the red matrix and 0 times the second row of the red matrix. So that is just 1 here. The second row of the product is minus 1 times the first row plus 1 times the second row. So that is using the row picture. So I do get this matrix by applying that blue elementary operator on my red matrix. So let me give you a few more elementary matrices. Suppose I want to swap the second and third rows, R3 and R2. This, of course, have 3 rows, so it's a 3 by 3 matrix. The elementary operators are always square matrices. So I take the identity matrix, which was 1, 1, 1. I swap the second and third rows. I get this, E1. There's nothing more to it than that. Scale the second row by 4. Take the identity matrix. Scale the second row by 4. And that is the matrix corresponding to the elementary operation specified there. Subtract 3 times the first row from the third. So nothing happens to the first row. Nothing happens to the second row. The third row, subtract 3 times the first row from the third row in the identity matrix, and that gives you the elementary operator. So keep that in mind. So what I said in the previous slide, let me put that down in black and white once more. The elementary matrices, also called the elementary operators, do the same operations that it did on A on any matrix that appears on the right of that matrix. In particular, they do the same thing on the identity matrix. So in order to get the elementary matrices, all you have to do is to apply the elementary matrix to the identity matrix, because EI is I. To put it differently, the elementary matrices all differ from the identity matrix by just one row operation. And the third row operation here does not change the determinant, because if you look at the matrix here, it's still a triangular matrix, and the determinant is 1 times 1 times 1. So that is still 1. But here, the second row operation, the determinant is 1 times 4 times 1. So that did change. Here, the determinant is 1 times the determinant of the submatrix here, which is 0 minus 1. So the determinant has changed sign. That is because we swapped 2 rows. So all those things fit in very nicely, don't they? Now there's one more complication. We want the inverse of the elementary matrices. So inverse is a topic that we haven't covered yet. But as you can imagine, inverse is a matrix that does the opposite of what the original matrix did. If you take A and apply that to X, so you get something. Then suppose you apply A inverse on it, you want to get X back. What does that mean? That means A inverse A has to be I. So if you can find a matrix such that when multiplied with the original matrix, you get I, then that matrix that you found is the inverse, which is what I said here also. If BA is I, then B is considered the inverse of A. If A is equal to B, A inverse times A times X is I times X, which is just X. So A inverse actually literally undoes what A did. And also you can write X as A inverse being run on B. So if you have a matrix that swaps 2 rows, R3 and R2, how do you find its inverse? Just do it again. Do it once more, then you get the original one back. So for this elementary operator, the inverse is the same as itself. The second elementary operator that we looked at, corresponding to the second ERO, scale the second row by 4 as an example. Then how do you undo that? Scale it by 1/4. So inverse is just scaling it by 1/4. So E2 is that, scaling the second row of the identity matrix by 4. E2 inverse is just scaling it by 1/4, the second row. Subtracting 3 times the first row from the third. How do you undo that? Add 3 times the first row to the third. So inverse is just flipping the sign of the first term in that expression. E3, subtracting the third row from the first row of the identity matrix, so minus 3 there. Adding the first row to the third row of the identity matrix, you get 3 there. Now, with those things in our arsenal, we are ready to look at what we call the LU decomposition. If we can do Gaussian elimination with no row exchanges, then the decomposition is A equal to LU, meaning it's just 2 matrices multiplying. We saw that the REF is already U, and then we just have to know what L is. So we are not doing any kind of row exchanges, and we never did any kind of row scaling. So we're using only the third elementary operator. So you saw that the elementary matrices were all lower triangular matrices, like here. If you're subtracting the first row over the second row from the third row, the elements populated will be here. So there will always be a lower triangular matrix. Then the product of a bunch of lower triangular matrices also is a lower triangular matrix. This is an exercise, I believe, that we will ask you to prove in class. And the inverse of the product also is a lower triangular matrix. So in order to get the REF, we applied a bunch of elementary operations, E1, E2, up to EK in that order. Then once I have the REF, all I have to do is to multiply by the inverse of the elementary operator, which is why we spent some time understanding what the inverse of elementary matrices were. And since the inverse of the elementary matrices of the third kind, the third row operations, is a lower triangular matrix, so that becomes a lower triangular matrix L, and REF is an upper triangular matrix U. So A has been written as product of 2 matrices L and U. So this is the LU decomposition of the matrix. It's the first of many decompositions that we will do in this course. This is one of the most foundational ones. So L encodes all the row operations, but in the inverse form. It's the inverse of all the row operations that we applied on the matrix A. And we saw that U can be used to get the complete solution of the system of linear equations that this matrix A represents with the help of a constants vector. So that is back substitution. U can also be used to get the determinant of A. Since we did not perform any row swaps, this U in LU decomposition will give you the determinant including the right sign. And since it's a triangular matrix, it's very easy to compute the determinant, which is the product of the diagonal elements. And this is the algorithm to compute the determinant in a most computationally efficient fashion. Doing it using Laplace formula would be a very bad idea. I said a pivot missing I meant a pivot missing in the diagonal position, diagonal location, which means the product of the diagonals will be 0 because that particular location would be 0. It cannot be anything other than 0 if one column doesn't have pivot. So a few examples here. Start with this matrix. I want to get to its REF. The first thing I want to do is to subtract from the second row 2 times the first row. So R2 gets minus 2R1 plus R2. So the operation for R1, it doesn't change at all. For R2, it is minus 2R1 plus R2. I'm applying that to the identity matrix to see this. R3 gets minus R1 plus R3. R3 is there and minus R1. So the first element is minus 1. Again, just apply it to the identity matrix. So that is the elementary operator. The inverse operation will be just adding. So 2 comes there instead of minus 2 and adding row 1 to the third row. So instead of minus 1, I get 1. After having done that, what I'll have is a 0 here. So I made that 0 and a minus 1 here because I subtracted 2 times the row 1 from the second row. So minus 2. So that becomes minus 1. Then I subtracted first row from the third row. So this 3 becomes 2 because I'm subtracting 1 from it. Similarly, this becomes minus 1 and minus 1. Now I need one more operation. I need to get rid of this. By get rid, I mean I need to make that 0. So I just multiply the second row by 2 and then add it to the third row. So multiply the second row by 2 and add it to the third row. Let me start from the top. Nothing happens to the first row. So first row is 1, 0, 0 in the identity matrix. Nothing happens to the second row. The identity matrix, it's 0, 1, 0. So that stays as it is. But the third row changes. I'm taking 2 times the second row, 2 times the second row and adding it to the third row. So 2 times the second row in the identity matrix is a 0, 2, 0. Add to the third row, which was 0, 0, 1. So I get 0, 2, 1. So that's how I computed the elementary matrix. Now the inverse would be just subtracting 2 times second row from third row. So instead of 2, I'll get a minus 2 here. Now L, as you know, is E1 inverse times E2 inverse. Remember, the order is going to be flipped because you're taking the inverse from one side to the other. Think about it. So when you multiply this and this, I'm claiming that you will get this. Then U is the REF, which we obtain by actually performing these operations, which is right here. So that's an example. There are more examples in the textbook. Please go through them and also work out some of those things either from the textbook or from the problem sets in the class. Now there's a slightly more complicated decomposition, that is a PLU decomposition, because there are times when you have to actually use the swapping. You cannot get away from it. So you can actually separate all the swappings and gather them into a permutation matrix, and the reason is explained in the textbook. Please take a look at that one. Permutation matrices are not lower triangular matrices, which you can see by just swapping 2 rows of the identity matrix. If you swap the second and third row, there are elements above the main diagonal and below the main diagonal. They can all be combined into one P and then L and U as before. That is a PLU decomposition. P for permutation, L for lower triangular, U for upper triangular. In this case, the determinant of A is going to be plus or minus the determinant of U, and the plus or minus will come from this sign of P. P keeps track of all the exchanges, and that gives a sign of the determinant. By the fact that the determinant of a product is a product of the determinants, you can see that the determinant of A is a determinant of P times the determinant of L times the determinant of U. L did not contain any operations that change the determinant from an identity matrix. Each one of the elementary operators within L was just a single row operation on the identity matrix which did not change the determinant. So the determinant of L is 1. So the determinant of A is determinant of P times determinant of U. That means plus or minus determinant of U. So if you had used the second ERO, then we would have had to keep track of the scaling factors also. Well, luckily for us, we didn't do that. Now, a couple of more words about the permutation matrices. So we can actually write down all possible permutation matrices in R2 and R3. You can actually compute the determinant of each one. So single row exchanges, the inverse is the same as it itself, and that has a special name for it, and that's called involutory. So the inverse of a matrix, if it is the same as itself, then that is involutory. That means if A is involutory, A times A or A square is I. The single row exchanges are all involutory because if you do it twice, you get the original matrix. R1 and R2 getting swapped, R2 and R3 getting swapped, R3 and R1 getting swapped. You just do the same swap in the identity matrix of the same size, and that's what you get. Now, if you do multiple exchanges, then it is not involutory. Of course, if you do it twice, you don't get the original one back. And this particular matrix, what's its determinant? What do you think it will be? 2 row swaps. So the first one gives you a -1. The second one gives you one more -1. So it's actually +1. So even number of row swaps, you get +1. Odd number, you get -1, which is kind of interesting. What it is telling you is that if you take a matrix and perform an odd number of row swaps, permutations, you cannot get the original matrix back because the determinant has a different sign. I think we said that in the previous video, probably last week's video. Now, one example of PLU decomposition. Suppose you perform the operation R2 and R3 getting swapped. Then, of course, that is the elementary matrix, R2 and R3 getting swapped in the identity matrix, and the inverse is the same. Then you can perform other operations to get to the upper triangular matrix, the REF. And if you look at L, that is indeed a lower triangular matrix, U is an upper triangular matrix, and P, that is just one row operation that we performed in the first step, swapping of R2 and R3. So that is the PLU decomposition. PLU, multiply those things, you will get A back. In the textbook, we do have a few more examples, and also the visualization, as you saw, that performs Gaussian elimination for you interactively for any 5x5 matrix that you can type in. So please go through the section 4 of the textbook. I'm not going to create a video for the examples, so please go through that and understand how it works. One thing I want to highlight as I'm wrapping up this chapter is the fact that Gaussian elimination is such a foundational algorithm, foundational process in linear algebra, that if you get a problem, any kind of problem, not merely for this chapter's problems, any problem that you might come across in the final exam or whatever, if you get stumped, you cannot figure out how to get started, one thing to try is to just perform Gaussian elimination on that one. That will probably give you some ideas. It is that foundational. So please keep that in mind. Please don't forget this. Don't tell me after the final exam, I saw this problem, I had no idea how to get started at all. If you don't know how to get started, do Gaussian elimination. And that is one way to get started. Even if you don't see how that connects to anything else, do that first, and then you will start saying, maybe that is how you get to the proof of that, or how to compute that complicated determinant or something. Gaussian elimination is so foundational that you have to try it on every single problem. If you already know how to solve it by looking at the problem, sure, go ahead and do it that way. But if you cannot figure out how to get started, this is it. This is the way to get started. That brings us to the end of chapter 4. Only 3 videos today. Next week, we will move on to chapter 5, which is Gauss-Jordan elimination. So it's a bit more than Gaussian elimination, and you'll see that it is actually the codification of Gaussian elimination plus the back substitution. And that has some interesting applications too. So see you in the next video.